What's going on, guys? Today I'm going to talk a little bit about CAN expander mass, some analog voltage sensors, and linear sensors, so to speak. Most of your pressure sensors are going to be linear. Position sensors typically are as well. And temperature sensors typically are not. There are some linear temperature sensors out there, but they're not very common. They're a little bit more challenging to do with CAN expanders. You typically have to use a table and do a bunch of samples and sample it out. But I'm going to use linear sensors as the example here because that's what you're going to use with CAN expanders in most aspects. On the left here, I have a CanCheck CFE18 board. I'm just using it as an example. It has 0 to 5 volts as its analog input signal, and then it creates what's called a just a number. We'll call it this number is 0 to 1023. There is a reason it is that number, but I'm not going to get too deep into it. They have it scaled and mapped out to 0 to 1023. And I'm going to go through this PowerPoint too, just explain some things. So what does an analog voltage sensor do? It actually takes some type of measurement, whether it's pressure, position, temperature, whatever it may be, and creates an analog voltage value from it, right? And then the CAN expander takes that analog voltage value and converts it to a number. And that number is presented in a CAN message on the CAN network for whatever logging device or device to read that information when it's broadcasted. So we got to find what's called the slope and intercept. A lot of people didn't pay attention in middle school math class. I didn't as well. This was gone over a little bit. It was called MX plus B back in the day. That's what they used in school. But essentially, we're just going to have to map out some values here. And so the necessary information we need to have is essentially a low and high point from the peripheral unit to like some type of voltage measurement. And then the CAN expansion voltage sample scaling values on the voltage to their, I call it the ADC values, but they're numerical values that they correlate that to on the CAN bus network. So for sanity's sake, I have a pressure sensor 0 PSI at half a volt, 100 PSI at 4.5 volts. And we have a scaling of 0 to 5 volts with 0 to 1023 being the numeric result of said voltage values. I wrote a program to do this. It makes things a little bit easier for most people. So we're going to take our sensor input voltage low point value, so 0.5 volts equals 0 PSI. We're going to take high point voltage, 4.5 volts is 100 PSI. Our expander input voltage minimum it's basically what's the voltage scaling it has. It's 0 to 5 volts, right? And the CAN output minimum value goes 0 to 1023. All right, I'm gonna hit map and we're done. It is here. So our factor is 0.122100012. I have it cut and basically rounded to the eighth decimal place. But essentially, it's 0.122100012 PSI, as they call it, per bit. And the offset is -1 to -12.454212245 PSI. So if we had a value of 0, we would get this -12454 number. If that was presented on the CAN bus network, and then once it would go up by 0.12 all the way up to essentially 100 PSI or 100 PSI and whatnot. I'll have this presented and pushed out on the social media forums in various ways. I'll also spit it out to probably GitHub on my GitHub page. It'll be on Python on the GitHub page. It don't allow you to push executables, I don't think. But and I also may have it on my my website at Mint Performance. But yeah, if you want to download this to make your life a little bit easier, by all means. I mean, I know a lot of people are using CAN expansion devices. I know the CAN information is getting more and more commonly used in the motorsports world, and even at the hobbyist level, it's becoming more and more popular. So hopefully this will help ease the barrier of entry of understanding what information you need for like a factor and an offset if you have that information provided for whatever logging device that you have. Anyways, until the next one, y'all have a good one.